So the first thing you're going to do on this handout is look up the definition for these 4 terms. Center of curvature, principal axis, vertex. So you can see there's some math terms here, and focus or focal point. Please make sure you're looking up optics definitions. For focus, I'm not talking about mental energy concentrated on doing a task. Okay, so make sure it is an actual optics definition. So please don't just write down the first thing that pops up on your Google search. Okay, you're going to define those 4 terms. I've given you a diagram of those 4 terms here. Here is a curved mirror, and these straight lines off the backside are showing that that's the reflective surface. So this is a concave mirror. Your principal axis is the normal line. You guys just looked at that in your style lesson. The normal line is a straight line that is perpendicular to the curve of your reflective surface. It's what we do all of our measurements from. So that's just the principal axis there. And the center of curvature is here. If you guys look at this curved mirror, if I imagined it like a full circle, why do you think the center of curvature is right here?
Because it's like the center of the curve.
Exactly, Kira. It would be as though this curved mirror was a full circle, and this is the dot in the very middle of the circle. Okay, so it is exactly what it sounds like. It's the center of the curved surface. So if I'm looking at a concave mirror, my center of curvature would be right here in the middle of that circle. I'm going to show you guys this diagram in a minute, but I've given you all of the light ray rules that will hopefully make more sense as you work with an interactive tool here in a minute. Basically, what these 4 rules are saying is if you have light that is going parallel to your principal axis, it will always reflect through the focal point, through F. Number 2 says a light ray through the center of curvature just reflects straight back on itself. So I have this blue light right here going through C, it reflects back on itself. It is actually following the angle of incidence and the angle of reflection, but just easiest to think about it going straight through C. A light ray through F, so that's the green one here. If it goes through F, bounces back parallel. You have to follow these arrows. And number 4 is the angle of incidence. The angle of incidence equals the angle of reflection. Don't worry about memorizing these 4. I just want you guys to know where they come from in our interactive tool here in a minute. Whenever you have 2 light rays coming together or intersecting, that's where your image forms. That's when we see a reflection, when those light rays intersect. If I flip the mirror around backwards, if I look at the back of my spoon, here's all my light rays coming in. This is a convex mirror. My light ray rules are still the same. However, why is my center of curvature behind the mirror?
Because that's the side of the curve.
Exactly, Kira. So all I've done is I've flipped my curved surface around. Still, it's a circle going this way with the middle being here. So the light ray rules are the same, but you'll notice my focal length and my center of curvature are behind the mirror because the mirror curves this way. I'm looking at the back side of it. But still, a light ray parallel reflects through the focal point. A light ray right toward my center of curvature reflects back on itself. And a light ray parallel, oh, sorry, no, that's 3. A light ray toward F, toward my focal point, reflects back parallel. So these rules are the same. All they've done is just flip the mirror backwards, okay? So what we're gonna do is play around with an interactive tool, and we're gonna be trying to describe the image that forms. So I'm gonna go back to the sheet here in a second. I'm going to put into the chat the website link, and I want us to go there, and we're gonna play around this tool. So what you're going to be doing on this handout is I'm describing the object, where it's located, and also the focal length of the mirror. And you guys will play around with dragging the object along the principal axis, along the normal line. And you're going to see what happens to my image as it gets reflected in this curved surface. So this arrow is you, and you can actually make the arrow bigger or smaller. You can drag the little points around, but I'll leave it here for a second. I'll just drop it somewhere. This is you looking in the concave part of your mirror. You guys said that when you looked in the mirror, or in the spoon, your image was upside down and small, right? So when I held that spoon far away from me, my image was upside down and small. As I brought the spoon closer to my face, my image was still upside down. It just got a little bit larger as I brought it toward my face. That's because of these light ray rules here. Parallel to the principal axis always reflects back through the focal length. And a light ray through the focal length hits the mirror and always reflects back parallel. And then this third light ray rule is showing going through C, or going through the center of curvature. You only need 2 light rays to find where that image is intersecting, but this diagram is actually showing you 3 light ray rules. The one they don't show you is the angle of incidence and the angle of reflection. So I'm just going to show you this other interactive tool, but you don't need this one. This one here, you can see shows the law of incidence equals the angle of reflection. This is a concave mirror. Most of the time, my image is upside down and quite small. And actually, with this interactive tool, I can turn on more light ray rules. But I really wanted you guys just to see that also the angle of incidence would equal the angle of reflection. So let me show you guys what you're doing on your handout. Okay, so take a look at that PDF that you've got there. I have go to that website, check. Place the object at the correct location with the correct height described in the problem. Make sure the focal length is correct, and then you're going to draw the ray diagram on here. I do want you to use a ruler or a straight edge today, so you might have to scrounge around your house to find something. Use any kind of a straight edge you can find. And I'm going to go over number 5 here in a second, complete the SALT table. So problem number 1 says draw the ray diagram for an object that is 2 units tall, placed at 7. 2 units tall, placed at 7. So I'm going to take my object. I'm going to make it 2 units tall, and it needs to be at 7 on my principal axis here. Hopefully you guys can see right here, my object is 2 units tall and it is at 7. You don't need to worry about that this side of the line is negative and this side is positive. It just is a graph, a Cartesian plane. Don't have to worry about that. This is a concave mirror. My object is 2 meters high. The object is placed at 7. Any questions so far?
Do we have to draw the lines exactly like that on our diagram?
Yeah, hold on one second though, because we're not done. Anyone have a question about how to get the object to the right height and to the right spot? Okay, the next thing I need to do is check my focal length. In my problem here, it says the focal length should be 4. So I'm going to show you guys how to move the focal length if you need to move the focal length. The focal length is actually at 4, but if it was not at 4, you need to put it at the right location. I can drag that dot, but I want the focal length at 4. So the object is 2 meters high, it's at 7, my focal length is at 4. Now the instructions say draw those 3 light rays. So you can see the one from the top goes straight to the mirror. So go right along the height of 2 and then draw it through the focal point. I have this, I'll do the second one here. From the top of my object through the focal point, it hits the mirror and bounces back parallel. This third one is going from the top of my object through C, through the center of curvature. So that's what that one is. All of them intersect at this point. So here is my image. My image is formed from the principal axis down to the intersection point. So you're going to copy this diagram on the sheet. Okay. Any questions so far? You're going to copy that on this handout. All right, now number 5 says complete the SALT table. And you might be like, what is that talking about? When we are describing an image in a reflection, S stands for size. Is my image larger, the same size as my object, or smaller? So S stands for size. The S in SALT is size, bigger, smaller, or the same. A stands for attitude, and I don't mean does it have a negative attitude or a positive attitude. This just means is it upright or inverted upside down? Is it upright or inverted? Location means describe to me where it exists on my graph. So we're going to do this together here in a minute. L stands for where does it exist? Where is the image forming? The type is a weird one. If the image and the object are on the same side, and you might want to write this on your handout. If the image and the object are on the same side of the mirror, it's a real image. If the image and the object are on opposite sides of the mirror, it is a virtual image. So when you're filling out this chart here, focus on the image that is formed and you're comparing it to the object. So I'm just going to go back to the website here for a second. If I look at my image here, when my object is 2 units high, sitting at 7, and my focal length is 4, focus on this image here. Okay, so I'm focusing right here. Is this arrow larger, the same, or smaller than the object?
Larger.
Larger. So next to salt on that first line, write larger. So next to the S for size, you're going to write larger right here. Okay. Next for attitude, you need to figure out, is it upright or is it inverted? Inverted means upside down. The object is pointing up and the image is pointing down. So are they both going in the same direction or opposite directions?
Opposite.
Opposite. So this is inverted. Next to attitude, write inverted. Location. So what I want you guys to do is just describe where is this located. The image on this diagram is between 9 and 10 centimeters. Just use a general description of where this is located. It's between, or sorry, not centimeters, units, because there's no units on this one. It's between 9 and 10 on the number line. Okay, the image is forming between 9 and 10. And now you have to figure out, is it real or virtual? So real means they're on the same side, virtual means they're on opposite. Is this image on the same side as the object or on the opposite side as the object?
Opposite.
Opposite. Sorry, of the mirror.
Same.
Same, thank you. They're on the same side. So this is a real image. This is the reason why. How does light interact with a mirror? Is it absorbed, reflected, or refracted?
Reflected.
Reflected. So it comes back toward the object. When you look at yourself in a mirror, the light hits the mirror and it reflects back to you. So the image should form on the same side because it should hit the mirror and reflect off of the mirror. Okay, so this is a real image. So you should have, it's larger, it's inverted, it's between 9 and 10, and it is a real image. Any questions on this one here with the salt or how to interpret this diagram?
So when it's curved this way, it's real. When it's curved the other way, it's not real?
No, that's not, I don't want you to interpret it that way. If the image and the object are on the same side of the mirror, it's real. If the image is behind the mirror or on the opposite side of the mirror, it's virtual.
Okay.
So I'm just going to show you guys how you'll do number 2, but then I do want to give you guys some time to work on this. And I do actually need to show you how to switch it to a convex mirror. So if you're going to do number 2, it says draw the ray diagram when the object is 1 unit tall, placed at 2 centimeters. 1 unit tall, placed at 2. So I would drag my object. I want it 1 meter tall or 1 unit tall. And I'm going to put it at number 2 right here. 1 unit tall, placed at 2. And I just need to check my focal length. The focal length given to me is 5. So I actually need to change my focal length this time. So make sure you check all of those numbers and make sure the diagram matches up. I need to change my focal length to 5. So my object is 1 unit tall. It's placed at 2. And my focal length is at 5. Look at this diagram for a second. All of the light ray rules are true. I have parallel and then reflecting through the focal point. I have going from the top of my object straight through C. And I have going through F and reflecting back parallel. My light ray rules are all true. They always exist. They're always going to be exactly that way. But look at where my image is forming. Where is my image forming?
On the opposite side.
Yeah, on the opposite side of the mirror. It looks like my image is forming back here. Your brain perceives light to travel in a straight line. So your brain is tricked into thinking that all of these reflected rays are intersecting back here behind the mirror. So it looks like you're going to have a virtual image. Now you still see the image, but it's a trick that your brain is perceiving the light to continue traveling in a straight line. So your brain is perceiving the light to go through the mirror. Well, clearly it's not. It's going to reflect off of the mirror, but the brain perceives a virtual image back here. So if you were going to describe the salt, is the image larger, the same, or smaller than the object?
Smaller?
Larger.
This arrow is bigger than this one, so the image is larger. Is it upright or inverted?
Upright.
Upright. They're both pointing up. They're both pointing the same direction, so it's upright. Where is the image located?
Between 3 and 4.
Good, between 3 and 4. And if you guys wanted to even jot down between 3 and 4 behind the mirror, so that it's complete, that like for you to understand it, that's fine. It's back here. So would this be real or virtual?
Virtual.
This one is a virtual image. So when you get down here where it says convex, you need to make sure that you drag the object to the convex mirror side of the diagram of the interactive. So let me show you what I'm talking about. Everyone, please look at convex mirrors. Draw the ray diagram for an object that's 2 units tall. Is placed 6 centimeters in front of the convex mirror. So 2 placed at 6. So let me go to the website tool. What you're going to do with this tool now is you need to take the object and drag it over here to the right side, or what looks like the positive number line on my diagram. You want the mirror to be bulging toward my object. So everyone look at my screen. Please look at my screen for a second. Initially, the website is set up so the object is on the concave side. Grab the object, the one that's labeled object, drag it over on the opposite side of my, to the positive side of my Cartesian plane. And now the mirror is bulging out toward my object, making a convex mirror. Any questions on how I did that? Okay, now it said to make sure it's 2 units tall, placed at 6. 2 units tall, placed at 6. So I'm going to put that there. And I got to check my focal length. My focal length is 5. Where do you guys notice your focal length is?
On the opposite side.
Yes, it's going to be back here. So I'm going to drag my focal point to 5. Here's my image. The light ray rules are still true. It just looks crazy. In a convex mirror, the light rays hit my curved surface and bounce out so that they spread out. They are diverging toward the object, so they converge behind the mirror. They're actually going to intersect behind the mirror. So if I look at my image, is it larger, the same, or smaller than my object?
Smaller?
Smaller. Good. Is the attitude upright or inverted?
Upright.
Upright, because they're both pointing the same direction. They're both pointing up. Where's it located?
Between 3 and 2.
Fantastic. Between 2 and 3. And is this real or virtual?
Virtual?
It's virtual because the object and the image are on opposite sides of the mirror. It's like the image is forming behind the mirror. It's tricking your brain, okay? Guys, please look at my screen for a second. With a convex mirror, does the salt ever change? Does it ever become not smaller, upright, behind the mirror, and virtual? Does the salt ever change?
No.
No. Convex mirrors always create a smaller, upright virtual image. It doesn't matter what I do to my object, the image is always smaller, okay? It is always upright, and it is always behind the mirror. Somebody said when they looked at the curves part of their spoon that it actually gave you a broader perspective around you. Can you guys think of where do we have convex mirrors in our I almost said everyday life, but maybe in our normal life? Where do we see these kind of mirrors?
Is it like a car mirror? Like is you can see around you?
Yeah, so your passenger side mirror of a car, you know how it says objects in the mirror are closer than they appear? They are a convex mirror. They give you a broader view so you can see more of what's on the side of the passenger side of your car.